Turn to the page, it says a closer look. Turn to the page, it says a closer look at continuous compound interest.
I got this stuff down.
I know you do. I'm about to change that though, sorry. But if you have that, I just got to add one little thing, but it's just going to be kind of like, I'm going to mess with this.
Continuous compound.
Yeah, I'm going to mess with it.
Oh my God.
I'm gonna push your brains through the ringer Friday at 1:30. You're not gonna push it. That's all right. We got Monday too. Also have a calculator out so you can help me do some calculations, which can just be your phone. And of course, something to write with, because you'll see on this page, right, the one that says a closer look at continuous compound interest. What I want to try to do is, like, I could just give you the formula, but you would have no idea where it came from, or there's a number that you've never seen. I got to show that to you as well. If I just gave it to you, I think you'd be like more confused. You know, sometimes it's like, I'm just going to tell you, you're going to believe me. I'm the guy at the front with the marker, so you just take my word for it. I don't know, like sometimes I want you to see where this stuff comes from. So I think you'll understand it maybe a little bit better. At the end of the day, you still might be confused about what I did to get there. That's okay. But you'll have a formula that you can rely on, and we can talk about it some more on Monday. So I'm pushing the due date for this whole class of 4.5 back to Monday. We'll have Monday to finish it up. We're just going to do this page right now. We're just going to do this 1 through 7 here. And I want you to notice at the top of this page, so before you even get to number 1, I'm going to do that here. You can see the setup, okay? The reality of finance is that interest is not really compounded like semi-annually and quarterly and weekly, daily. Sometimes it's daily. Usually it's monthly, sometimes daily. But more often than not, it's actually compounded continuously. Like so often we cannot count the number of times that it's happened because the number's so big. And so I want to kind of take one simple, easy example, starting with $1, getting 100% interest just for a year, and messing with n, going from annually to monthly to daily, and like go like higher and higher and higher, and seeing what happens to the result. We're going to use that result to come up with the formula. So the thing that I want you to notice is how much of this is going to stay the same over and over again. Okay, initial deposit of $1, so P is 1. Okay, and a rate of 100%. Okay, so here's our original formula. I'm actually going to go like above number 1. You can kind of put it off to the side. Like there's a little spot like right over there, like under the word continuously. Like don't put it with number 1 yet. I just want like a model in terms of T. I want to do an A of T. I know I might be up in the glare a little bit, folks at home. So let me know if you can't see that. Actually, that one's okay. I think 1 might be in the glare a little bit. Okay, P, very cool, $1. Just 1. I'm trying to make it easy to come up with this, okay? And then 1 plus, because compound interest, just the number 1. So, okay, now the rates, right? So I'm just using this. T1, 1 plus, okay, the rate. 100%. Like 5% was 0.05. 1. 25%, 0.25, 1, like 100, like 1.00, so just the number 1. 100% really just means 1. Now, I'm going to leave n just as n right now because it's going to change. Look, annually, monthly, daily, hourly, it's going to change as we go. So I'm going to keep n in there and then put nt up here, okay? But you're going to see that I'm going to leave t as just 1. We're just going to go out 1 year and see what happens. Okay, so with like 1 through 7, we actually won't get to 7 just yet. We'll see how far we get. 1 through 6 for sure is just going to be A of 1. So, okay, so number 1, A of 1. Okay, number 2, A of 1. Number 3, A of 1. But I'm going to change n as we go to see what happens. Okay, so 1 times 1 plus 1 over. So principal 1, 1 plus, a rate of 100% over, what was number 1? Was it annually? So how many times per year does annually mean? Yeah, 1. 1's all over the place. N is 1, T is 1. It's just 1, 1, 1, 1, 1, 1, 1. Trying to keep it simple. All right, now what is that? All right, well, here, let's slow down for a second. Slow down. 1 times some stuff. Does that 1 make a difference? All right, I'm dropping. 1 plus 1 over 1. 4. Okay. To the power of 1 times 1? Another 1. Okay. What's 1 plus 1? 2. Now that kind of makes sense. Start with $1, get 100%. Now I have $2. I have double. Okay, cool. So that's the first one, $2, right? 100% on my $1 means I get another $1, so I have a total of 2. All right, now all I'm going to do is I'm going to keep everything else the same. And if you're cool with it, I'm not going to, this 1 doesn't change anything. So I'm not even going to keep that in there. So 1 plus 1 over, so it's like that one's right here. I'm just not keeping it. I'm just saving this a trouble. I want to change N. Okay, I'm going to change N from annually now to monthly. So what is this? What is this number, that number? What are those going to be if it's monthly? Well, 12. Now, it's going to be 12 times 1. Okay, cool, just 12. Here's where I'm going to start needing your help. Now, I still want you to write this all down, but if you can type it in for me, because we had some issues, people typing it in wrong during 6, and it actually helped people figure out what they're doing wrong, so it was kind of nice. If a bunch of us type it all in, we make sure we get the same answer. We can round. It's probably going to be some kind of decimal. I just want to see what happens. Like, does it go up to like 3 and 5 and then 10? Like, is this going to just keep getting bigger and bigger? Like, can I turn $100 into $100 just by like increasing how often I get paid? What do you get? 1 plus 1 over 12 to the 12.
2.61.
$2.61. Nice. So I turned. All I had to do was get paid monthly instead of once a year, and I made an extra 61 cents. Now, I know we're talking like tiny little amounts here, but what if it was like $100 or $1,000 or $1 million? It's a huge, huge difference. So we jumped up 61 cents. That's a big, big, big difference. Nice. Okay, I like that, right? All you gotta do is pay me more often with the same rate, same starting amount, and I'm getting paid a whole lot more. And so the question is, like, does that keep happening? Like, does it become like 80 cents and then like $3? Like, can I really like make this thing grow really, really, really fast just by changing how often we get paid? 1 plus 1 over, that's the only thing I'm gonna change, right? 1 right there, right? Rate of 100%. I skipped weekly just because I kind of ran out of space. Plus, we don't really need to. Daily. What number should I put? 365. Now, sure, it's like 365.25 realistic. But we'll just keep slightly easier round numbers. Because you actually might recognize some numbers as we keep going. $3, $5, $10. I mean, from 1 to 12 was a big jump, but now 12 to 365, that's a huge jump. How much is it? $2.71. That is not a very big difference. Now, were there more decimals after that? Yeah. What are? Give me a couple more. 2.71. Anybody have it still sitting there? Jared, what do you got?
4, 5, 6, 7.
That's cool. 1, 2, 3, 4, 5, 6. Let's do like one more again on.
4.
4, cool. So 7 decimal place. It's way more accurate than money ever is, but just to see what kind of changes we've got. So we went from gaining 61 cents to gaining like 10 and a half cents. And we went from monthly to daily. That was a big jump in how often I get paid, and I didn't really end up making that much more money. But it still went up, I'll take it, right? Still going up, so I like that. All right, cool. Now, again, 1 year, let's do 1 year. 1 plus 1 over, let's get paid more often. Let's get paid every hour. How many hours are there in 1 year? Not in 1 day, but 1 year.
8,760.
How'd you do that?
I used Google.
Use your resources, right?
Yeah.
How would you do that without Google? If you knew that there are 365 days in a year and 24 hours in a day, both fine together. Yeah. But she's right, absolutely. 8,760. All right, so I gained 61 cents. Now I gain 10 cents. Again, I'm going to round it because it probably goes on way longer than this. Let's see if I gain like another 10 cents or maybe 15, or because look at that difference. That's huge. 24 times difference. Big, big difference. 1 plus 1 over 8,760 to the power of 8,760.
It's $2.71. Well, do you want like a
Yeah,
long
give me some more just to
Okay.
see.
Sorry, 71812
Sorry, 7181.
2669.
Cool. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. That's right. Gained 61 cents. Gained 10 cents. Now, not even half a cent. You think this is just going to keep growing and growing and growing and growing? Or are we starting to slow down big time? Big time, right? We shot up real quick and now we're starting to level off a little bit. And all we're doing is we're changing how often we get paid on the same amount. But the problem that happens is as we make this number down here really, really, really big, this whole fraction is really, really, really small, right? 1 plus, this is almost nothing. Like almost nothing. Yeah, we can multiply it by itself a lot of times, but it's basically just the number 1, like a little bit more than 1 times itself a whole bunch of times. I think we got 2 more. How many minutes are there in 1 year?
19,525,600.
Where'd you come up with that?
Google.
Good old Google. Right? This times 60 seconds every minute. You ever heard of this number? 525,600. Does that ring any bells? Anybody in this class? 525,600 minutes. You heard that? Now let's sing the tune.
I know.
From the Broadway play Rent, one of the most famous pieces of art in the entire world. Okay? Or it's from The Office. To the power of 525,600. Very good play. You guys should check it out. This is a movie original. Actually, with a lot of the original actors. It's about the AIDS epidemic in New York City in the 80s.
Which office is it? The American Office?
Yeah, it's the American Office. It's the one of the last episodes of season 7. Yeah. Okay, somebody help me out.
2.718279 or 924. Sorry.
That's good. 924.
Yeah.
Look at how many numbers keep staying the same. 2.718. Okay, that's the only change is now 1/100th of a penny difference and a half. How many seconds are there in 1 year?
31,536,000.
That's right. 31 million. Is that what it is? How many zeros? 566, right?
Yeah.
566, my bad. 31
No,
million.
536.
536, thank you. 31,536,000. 1 year, you experience over 31.5 million seconds. It's kind of crazy. Now you're asleep for a third of them, so 20. You think this number's going to get a whole lot bigger?
No.
Look at how close they are. Let me help you out. 2.7182 315 36000. think those are the same.
I'm sorry.
Well, it shouldn't just be you. It's a big number. It's a really, really big number. 31,536,000. Should be pretty close to that. Like, these are really, really close. 2.7182, maybe 8. 177, blah, blah, blah. These keep going. What happens is this number starts to level out big time. In the first like 4 or 5, and then keep going, right? Every 10th of a second, 100th of a second, millisecond, nanosecond. This becomes the same number over and over and over again. The decimals start to what's called converge on a number. Now, what's happening is n is getting huge, like really, really big, really, really fast. But the answer that we get from that is not getting as big. It's actually slowing down how quickly it's growing. And you'll see that, and I'm going to show it to you, like this number levels off. And it gets to a point where it can't get any bigger. Okay, this is called an infinite sequence, right? Because the numbers just keep getting bigger and bigger, and we can do this forever. And so what's happening is we're messing with, really, and so maybe put this maybe off to the side on the right somewhere. What we're doing is we're just messing with this. 1 plus 1 over n to the n, right? Yeah, remember I picked the letter n to mean the number of times, right? I just made that up. But it keeps getting bigger and bigger. And bigger and bigger and bigger. But it doesn't, like, the answer doesn't. It's starting to slow down. It's starting to converge. Even though n keeps getting bigger and bigger, how could we say n just keeps getting bigger and bigger and bigger and never slows down? Just the number down here, just this. N getting bigger and bigger and bigger and bigger. N approaches, it is heading towards. Okay. As n approaches infinity, like we're just going to go this way on the number line forever. You see what happens? That result, 1 plus 1 over n to the n, does not keep getting bigger and bigger. What happens is that this number actually, like this sequence, this whole infinite thing, I know I'm giving this to you on a Friday, just wait, I don't even know. You actually approach a number. But you can see that this number doesn't really have much pattern to it, right? Kind of bounce all over the place, like pi and square root of 3 and stuff like that, right? So there's a number that we're actually getting close to. It's just a number you've never heard of, okay? Now, this number that I'm about to write right here is approximately 2.71828, 1828, 45, 90, 45, blah, blah, blah. The repetition there is actually kind of sneaky. It's not really repeating the 2.7, 1828, 1828, 45, 90, 45. That's just a luck that it worked out that way. After that second 45, it just starts bouncing all over the place. It's definitely irrational, like pi and like square root of 3, stuff like that. It's a number. It's just one you've never heard. And it comes from this. Like the guy that discovered this, created it, whatever you want to call it, named it himself. Okay. This is called. I'm gonna give it a name here in a second. Here's the guy. Okay. He was a little vain, called it after himself. So the mathematician's name is. That's a U. So kind of looks like Euler, right? It's actually pronounced like Euler. Euler's number, but it looks like Euler. You know what he called it? It's not because of what you think. He called it E. Not after himself. I think, so the legend goes that he had already used A, B, C, and D for something, and so he had gotten to E when he discovered it. Okay? Like pi is a Greek letter. We don't recognize it as being a letter because we only think of it as a number. It's actually really a letter. Just like E we recognize as a letter, it's a number. And it's 1 plus n, 1 over n to the n as n goes to infinity. And it's on your calculator, and you need to know where it is so we can use the formula. Okay? So open up your calculator, wherever you got it. And it's really similar to pi in that this goes on forever. There's not really any pattern to it. You're right, pi is 3.141592653589793238462 blah, 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 blah. It goes on forever. Same thing with this one. Do you know where pi is on your calculator?
Over the division, over the slash.
The pi?
No.
Where's pi? Let's start with pi first.
Little arrow.
Over the, like the up arrow into the exponent. Okay, so where's E?
Over the slash.
The button right below. Okay, over the division button. So, like, go to your calculator, like, clear it out so there's nothing in there, and do second division. Press the blue or yellow second button, whatever you got, and there it is. 2.718281828 46, because it goes 45 now. Okay, that's the number E, and that is part of our continuous compound interest formula. The problem is it's not the only thing, right? Because look, 1 plus 1 over n to the n. All right, well, what about P? What about R? And what about T? Right? We need all those. I need to know what I'm starting with, what my rate is, how long you're going to let me do it. All I know is that n is infinity. But it's not really, because it's not a number. But it's going to go in that direction. And I don't have an infinity button, so I just can't use compound interest and do like 1 plus r over infinity. So what I have to do is mess with that compound interest formula to come up with a continuous one. Okay? And here's where I think what I'm about to do is hard enough to follow just by watching, but to also write it down, I think that's up to you. I don't think you need to write down what I'm about to write down. Once I actually fill this box in, okay, cool, then you'll write it down. I just think it's kind of fascinating to see this proof work itself out. So I don't have to do something super, super crazy to prove it to you, but I am going to use this to do it. Okay? Questions about this, though? It's confusing enough, I know. And don't worry, we have Monday to talk about it some more. I just want to show you some of the things that we can get to and where this stuff comes from. As nice as it is sometimes to be like, just tell me what it is. I want you to believe it a little bit. Okay, so Euler's number, we're going to use it. All right, so check this out. Okay, compound interest looks like this. P 1 plus r over n to the n. Now, I'm going to do something. This was not my idea. I figured out this proof. Somebody else did it, okay? But I'm going to use an idea to get myself there. Write it down if you want. You'll never have to recreate it, but if you feel like following along. You know how I just picked n? It's like, oh, it's a number. I'm just going to call it n. That was my choice, right? I'm going to do something else that's my choice. I'm going to let m be whatever I feel like. I chose n, right? I'm going to choose something for n. I can pick b or q or what. I'm just making that. But I'm going to pick something pretty specific. I'm going to take this fraction and flip it. And you'll see why. I'm going to use it. Okay? And here's what I'm going to do, right? How am I going to get this back to this? Well, if I flipped it to call it m, well, I have to flip it back to get back to here. Well, or so I'm making this up. Like, all right, m equals whatever I feel like, but I'm going to use it. If I flip this, well, then I better flip this. I'm making this up. So if this is true, then that's true. I chose to do that. And you're going to see why. Okay? So here's what I'm going to do. I'm going to use it right here. 1 over m. Why? Because that kind of looks like this. Now I've got what I want. I got r out of this fraction. But check this out. What the heck do I put right here for n? Well, I've got this nice little equation that has n in it. Watch me isolate by cross multiply. 1 times n. What's 1 times n? And what's m times r? Well, m times r, and cross. So this n, no, it's really m times r times t. This equation and this one are the same because I let this happen. Now watch this. This is where the craziness comes in. P, I'm going to isolate some stuff by just putting some big old brackets to help isolate whatever. I want it to look like this. But it's not n, I made that up, it's just m. Okay, fine. 1 plus 1 over m to the n. That's what I want, because that's going to be e when I let it happen. To the, up here, like higher brackets up here, R2. What's the shortcut with exponents? When you raise a power to a higher power, what do we do with all this? Exponent raised to a higher exponent? Property of exponent. Exponent raised to a higher exponent. Like x squared to the third. What do you do with those numbers? Multiply. So m times r times t, right? M times r times t. So aren't these the same? Okay, now let this happen. Let's let, I called it m, n, p, whatever, who cares what letter I choose. I'm going to let the number of times I compound per year, whatever, I'm going to let this go to infinity. What do I get? 1 plus 1 over m to the m if m goes to infinity? What's all of this in here? That is the continuous compound interest formula. A of t equals p times, I put the dot there to let you know that the RT that's in the exponent, yeah, your exponent now has both the rate and time in it. That's only over the e. So we're going to use that second division. That e number is now our base. Okay, this right here is that number, okay, Euler's number, 2.71828, blah, 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 blah. Okay. Pretty crazy. Okay. And what does it have in it? It has P. Good, I know where to start. Rate, awesome, tell me how much I'm going to make. T, tell me how long to do it. But what's happening is that we're going to do it constantly, continuously. We are not going to stop getting paid. They are dropping money into our bank account. Not every minute, not every second, not every millisecond. Continuously. So often, we can't count how many times they've done it. They're going to do it an infinite number of times a day, a week, a month. You're going to do it an infinite number of times every second. An infinite number of times every millisecond. That is how banks calculate interest. Continues. Okay. P times E to the R. E is just a number. It's just 2.7 whatever. It's this, right? 1 plus 1 over n to the n as n goes to infinity. It's not approximately E, it's exactly E. An infinite sequence ends in a number that's less than 3. Pretty awesome. And that is enough melting your brains for one day. I think I will give you these 3.5 minutes to recover from what is actually a pretty straightforward proof of where this comes from. I know, right? The word straightforward does not sound appropriate at this point. Welcome to upper level mathematics. You just get started.
Oh my goodness.
Yes, sir. It's a good one. All right, again, nothing to submit today. I pushed back 4.5 to Monday. You'll look at the back of this page, you'll just see some continuous ones. We'll just try out. You'll have time to finish up whatever you didn't. I'm good to go. You guys at home are good to go. I will see you tomorrow. Or see you Monday. Have a good weekend. Remember, Mondays is a regular school day.